Okay. All right. So last time we talked a little bit about classical field theory, and we focused on the Klein-Gordon equation. And so those notes, will, like I said, they'll be in the Dropbox or be in the. I'll make them available to you guys. But what I want to do today is start to move towards the quantum theory of fields, and in particular, quantize the Klein-Gordon field. And you're going to see the way that we do this is in almost pure analogy to how we quantize the simple harmonic oscillator and just regular quantum mechanics. Okay. So the outline for today, and today might be kind of short because I just realized that I'm going to have to do PowerPoint presentations because I have a student at CERN that I have to record this for. So this is the only way to do it. So I just started writing these slides about 2 hours ago. So today's class might be a little short, but that's okay. I'll get caught up over the weekend. So what we want to do is we want to quantize the classical field theory, and we're going to, like I said, we're going to focus on the Klein-Gordon equation, and we're going to do this exactly, the way that we quantize things in regular quantum mechanics, which is basically taking any dynamical variables that you have, whether it be position or momentum or angular momentum, whatever, and promoting those to an operator, right? And then impose some type of canonical commutation relations. And then we're going to we'll try to solve the theory. In other words, obtain the eigenvalues and eigenstates of the Hamiltonian. And we're going to do this pretty, I would say, somewhat rigorously, but a lot of it's going to be based on the analogy of the simple harmonic oscillator. All right, so just recap of last time. You can recap last time in basically three equations. So we talked about the Lagrangian for a classical scalar field, the Klein-Gordon field, which is, so this is a non-interacting field. It just has a kinetic and a mass term, right? And then using the Euler-Lagrange equations of motion, you can derive an equation of motion for this field, and it's just the Klein-Gordon equation, right? And then typically, we don't work with the Hamiltonian in field theory, but today we'll find it useful because we want to try to solve for the eigenvalues and eigenstates of the Hamiltonian. So in other words, we're trying to solve the Schrodinger equation, okay, for a field. All right, and this is what we derived last time, just using kind of the analogy or analogous Hamiltonian for discrete particles, and we noted that the first term is a kinetic term. The last term is kind of like like a rest energy term. This is the energy from the field being, there in the first place. And the middle term is what we call shearing term. So that's a term that comes from the deformation of the field. Okay. All right. So let's get to it. Okay. And so as I was saying, we want to try to quantize the theory, and we're going to do this exactly the same way as we do in quantum mechanics. All right. So we're going to take our field and its conjugate momenta, density, phi and pi, and we're going to promote those to operators. Okay. Just like we would, if we were starting with, I don't know, the harmonic oscillator, we promote x and, we write it down classically, the Hamiltonian, and then we promote any dynamical variables or any observables to operators, right? So x and p, in this case, the field and the conjugate momentum. Then once we've done that, we impose some suitable commutation relations. So something analogous to, the commutator between x and p being I h bar or whatever it is, right? So here it is for the discrete case of regular quantum mechanics. And you note that I've already set h bar to 1, okay? So that will be the convention in this class. So any constants, h bar, c, the Boltzmann constant, the Jackson constant, whatever, they're all going to be 1, okay? And so this kind of summarizes the case for a system of discrete particles, the commutation relations between the dynamical the position variable and its conjugate momentum. And what we want to do is just kind of move to the continuous case, the field case. And when we do that, we can just write down commutation relations between the field and its conjugate momentum. Now these are continuous variables, so you're going to go from a Kronecker delta function to a Dirac delta function. But it's basically of the same form, okay? And you see that the fields and the conjugate momenta, they both commute with themselves. And these are implicitly they're same time commutators, okay? So these arguments here, x and y, are really the three vector, the position vector, and the commutators are understood to be taken at the same time, okay? Not that that'll ever come up a lot, but just to put it out there. Okay, so the fact that we're promoting the fields, the position and the momenta fields to operators obviously means that the Hamiltonians are going to become an operator, right? And that's what we're used to from regular quantum mechanics, right? And so what we want to do is basically solve, the Schrodinger equation, right? So we basically want to solve for the spectrum, the energy spectrum of the Hamiltonian. And then, we'll not only get the energy eigenvalues, but we'll also get the energy eigenstates. Okay. And you ask yourself, you go back and you look at that Hamiltonian, and you go back there, right? And you look at this thing and you say, okay, I don't even know where to start, right? And there's one of the rules in quantum field theory is, when in doubt, take a Fourier transform, okay? So if we transform, so these are the fields in position space. But if we can do a Fourier transform into momentum space, maybe we can make some progress. So that's what we try to do when I get there. Okay. All right, so we take a Fourier transform. So for example, the field in position space we write as a Fourier transform of the field in momentum space. Okay. And what does that allow us to do? Well, it allows us, because one of the terms in the Hamiltonian was the del squared term, right? And so now that del squared term, we're able to evaluate it because all the position dependence is in that exponential, right? So it's going to pull down, the del squared term is going to pull down two factors of IP, okay? Oh, and one thing that we're doing here, we're working with a real field, okay? So we have to specify that anytime we take phi star, it has to be equal to phi minus p, okay? And that's just so that the field is real. Okay. Do you guys have a question?
It's just a small one because we have a present whole label that covers last line representation.
Oh, so you can't see the bottom?
We see that F conjugate, phi conjugate is equal to phi minus p, and then the rest is.
Okay. So it says such that phi is real, is what it says. I'll try to keep that in mind when I write the future slides. Okay?
I think we should ask him to just remove that thing somehow.
Do you know what he's talking about?
This? Possible.
What are you talking about? Remove?
He said there's a on their screen. There's a label or something that's covered in this part.
There's a digital watermark.
Oh, that's going to be. You have to talk to Armando about that.
Yeah,
we're not sending that.
Maybe that's
Okay. All right. Okay. So let's do that. So let's take this Fourier transform for the field and plug it into the Hamiltonian and see what it gets us. Okay. So when we plug the Fourier transform of the field into the equation of motion, so I'm sorry, we're plugging this into the equation of motion, not the Hamiltonian. But if I plug it into the equation of motion, I can, the Klein-Gordon equation has the time derivative term squared and also has a spatial derivative squared. And so that spatial derivative we can evaluate on this Fourier transform. It's going to pull down those two factors of IP, right? And so what we get is something that looks like, kind of like a simple harmonic oscillator equation, right? Second order in time, and we've got some constant multiplying the field, right? And actually, if we can define a frequency that we'll call omega p, and it'll be the square root of that constant or that term multiplying the field. And when I do that, I get something that looks, almost exact. It is the simple harmonic oscillator equation, right? Where now, I mean, the main difference here is that phi is not a wave function; it's a field. But we can at least use, the analogy, the skills, if you will, that we learned in quantum mechanics about how do we solve the harmonic oscillator to try to solve this equation for our field phi. Okay, so it's just the equation of motion for the simple harmonic oscillator. So what we can do is try to apply what we know about solving the harmonic oscillator to this case. So let's just, refresh ourselves on how we do solve the quantum, or at least one approach to solving the quantum simple harmonic oscillator. And the way that we do it, well, we first write down the Hamiltonian. This is the p squared over 2m plus the potential term, right, the x squared term. And if you go back and you look in Griffiths, or you go back and look in Sakurai or some other book, you see that what you can do is instead of trying to solve the full differential equation, you can actually factorize the Hamiltonian. And factorize is in quotes here because it's not a true factorization, but you can use a trick where you rewrite x and p in terms of so-called ladder operators, right? And so you can rewrite x as the sum of some operator and its Hermitian conjugate. You can write p in the same way, basically, right? And then what you find is that you take the canonical commutation relation between x and p, and you can derive a commutation relation between this operator A and its Hermitian conjugate, right? And it's fairly simple. And actually, when you do that, you can plug it in, and you find that the Hamiltonian takes a very simple form, right? So this is the Hamiltonian for simple harmonic oscillator, right? So the omega here is playing the role of energy. Remember, I've set h bar to 1. Okay, so omega is the same thing as energy. The first term there, the A dagger A, we normally identify with the number operator, right? The number operator counts the number of excitations at each level, right, of the energy of the harmonic oscillator. And the last term, the 1/2, is we identify with the vacuum energy. Okay. So once we have the Hamiltonian written in this form, then we can start to think about how do we want to construct these states, right? So the easiest state to work with, or to start off with, is the ground state. Okay. So we can start with the ground state, which we denote as just a 0, right? And we can postulate that this A operator, whatever it is, it destroys the vacuum. Okay, so whenever A operates on the vacuum, it gives me 0. Okay, so that's our starting point, and that's just a pure, just a postulate. Okay, and then the idea is that you can actually build up the excited states by using the Hermitian conjugate of that operator, which we call the creation operator, or the raising operator, if you will. Okay, so we can create higher level states by operating on the vacuum with a dagger. Okay, and typically, you can go. I'm not going to go through the whole argument and the whole proof and everything else, right? But the idea is that you build up excited states by applying the creation operator. Right? So that means that if you build up these states in that way, when I apply the Hamiltonian to these states, I find that the energy is just of the same form as the Hamiltonian, but now the Hamiltonian, the eigenstates are really the eigenstates of the number operator, right? So when the number operator hits the end state, it just gives me back the end quantum number, right? The number of particles, or the number of excitations of that state, okay? And so that's the way that you do it in quantum mechanics, okay? And that should all be reviewed, and hopefully you've seen it several times, okay? So now what we want to do is, we've seen that the Klein-Gordon, the Klein-Gordon field obeys an equation that looks a lot like the simple harmonic oscillator equation. Okay, so we want to try to use that same approach, this idea of rewriting, our dynamical variables in terms of annihilation and creation operators. Okay. The big difference, though, is that now we're dealing with a field, right? A field that permeates all of space. Okay. So each Fourier mode, when we do this Fourier transform, each Fourier mode, which is denoted by the p variable, is going to be treated as an independent oscillator. And each independent oscillator is going to have its own set of annihilation and creation operators. Okay, so you think of it as, if you could discretize space at each point in space-time, there's a each point in space-time has its own A and A dagger. Okay, and those points in momentum space are labeled by the p variable. Okay. All right, so that's the complicating feature of trying to do it, trying to solve field equations using this. Okay? And the other implication is that when we write our fields in terms of A's and A daggers, we're not going to have this nice compact little thing in terms of one A and one A dagger. We're going to have to sum or integrate over all of those annihilation and creation operators. Okay. Or sum over all the Fourier modes, if you will. All right, so the way we do this is we want to use the analogy of the simple harmonic oscillator to write phi and pi in terms of A and A dagger. But we have to account for the fact that we've got this, we're summing over all the Fourier modes, right? And so this is a continuous variable, so you have to integrate over it. Okay, so you have the two exponentials multiplying the A and the A dagger term. You've got this constant factor, this 1 over 2 omega p that comes in, I think for Lorentz invariance reasons, I can't remember, but it's just a constant, okay? But you can see that I'm integrating over the volume of momentum space, right? And then you can just take a time derivative of phi to derive what the momentum conjugate density field is, right? And it looks basically the same, okay? You just got to change in units, so the prefactors are a little different, okay? In some of the calculations that you'll do for homework or whatever, a lot of times it's more convenient to make a replacement in this. So you notice that this integration is symmetric, right? It goes like p squared, okay? So that means that I could actually take p to minus p, and I wouldn't change anything, okay, in one of the integrations. And if I do that in those second terms, right, the label's obviously going to change on the A daggers. It's going to become A minus p. But what it does for you is it gives you the same sign in that exponential. Okay, so you can pull that exponential out. All right, and that simplifies your life a lot because when you go to compute the Hamiltonian or the momentum or whatever, you're going to be plugging these expressions in to the to the Hamiltonian, right? And then you're going to have to take derivatives, all right? And so if you only have one exponential there, it's going to cut down on your headaches, believe me. So it's a nice little trick to do, and there's nothing wrong with keeping the minus p there. In the end, you could go back and take minus p to p, but I think everything works out if you just keep it as minus p. Okay. Okay. So with those definitions, and then we take the canonical. Remember, on one of the first slides, we had the canonical commutational relation for the phi and pi fields. Well, you take your definitions of those fields in terms of the A's and A daggers, and you can compute the commutation relation for the A and A dagger, right? And you actually find that it's basically a generalization, if you will, for the discrete case. Okay. Notice that the difference is here we've got labels on our annihilation and creation operators because these commutations can be between different momentum space points. Okay, and so that gives you that delta function, that continuous Dirac delta function there. Okay, and the factor of 2 pi cubed just comes from the fact that you're integrating over volumes and stuff. Okay, but that just comes from taking the commutation relation for phi and pi and just plugging them in. Okay. All right, so now what we can do is we can take the expressions for our fields, right, our pi and our phi, and plug those into the Hamiltonian, take some derivatives, right, and see where it gets us. Okay, so that's what I'm going to do. I'm going to take pi and phi, and I plug them in, and I get this beast. Okay, which you can see that I've simplified things a little bit because I've used the little p to minus p trick. The other thing that you'll notice is that I'm being completely general when I plug in pi and phi, right? So I'm allowing those integration variables to be independent. Okay, so that's a common mistake when you go to compute these things is you think, oh, I'm just integrating over the momentum. I'll just use the same labels, right? I'll just call both of them p or both of them p prime, and that can get you into some trouble. Okay, so my advice is always to be as general as possible, and what will happen is you'll get Dirac delta functions that'll condense everything the way it should be. Okay. All right, so this is what we have to deal with. Okay, so this is a Hamiltonian, and typically what you do is you multiply this all out, and then you use that commutation relation between the A's and A daggers, or the A's or the A daggers, right? And you try to manipulate things and get it whittled down, okay? And after a little algebra, and by little I mean about probably 4 or 5 pages, you can get it down to an equation that looks like this, okay? And what you notice is that, if you look at it, it looks a lot like the Hamiltonian for the harmonic oscillator, right? But you can see the differences, right? So you can see that we still have the energy term here, which is omega p out in front. We've got something that looks like a number operator, right? It's the number operator for a particular point in momentum space, right? We have to integrate, so you see that we're integrating over all momentum space, right? Because we have these this continuous field now instead of discrete particles. And then finally, you have the second term there, which we would relate to the ground state energy, right? You see the 1/2, and then you see this commutator between A and A dagger, and they both have P as their subscripts, right? And if you go back and you look at this guy, right? You look at the commutation relation between AP and AP prime dagger. Looks like that. It goes like a delta function. Well, if they both have the same subscript, that's going to be a delta function of 0, right? Otherwise known as infinity. Okay? So you see what happens is that the second term gives you a delta 0 and subsequently will give you infinity. Okay? So the second term is giving you an infinite energy term. And the way we interpret that is that we're basically, that term is coming from summing over all the 0-point energies. So summing over all the ground state energies of every point in momentum space. Okay? That makes sense, what I'm saying? No? Okay. All right? So we've got this infinite term in our energy, right? And you might say that's a problem, right? It's disturbing. And I always make a joke that, at this point in the class, that you either get up and leave and become an experimentalist, or you accept it and move on and become a theorist, okay? It's just something that comes out of quantum field theory a lot. And, the way we reason, or the way that we can, accept it, is the fact that, in experiments, they can't measure, this infinite energy shift. All they can do is measure the energy difference between the ground state and whatever excited state you have. All right, so that shift, that infinite energy shift, even though it's infinity, is across the board. All right, so you can't detect this infinite energy shift. Okay, and so for now, because it's non-detectable, we'll just ignore it. Okay, and we'll see later on that these infinities pop up all over the place, and so we have to develop kind of an algorithm for taking care of these infinities, and that's what is known as renormalization. Okay. Okay. So we've got, what do we have now? So we've got, let me remind myself where we're at. Okay, so we've got a Hamiltonian. We can ignore that infinite energy term, and so now we can start to talk about how do we construct the states, right? So in the simple harmonic oscillator case, we started with a ground state, and then we built up the excited states by applying A daggers, right? So we can do the same type of thing here, okay? So again, we're going to define a vacuum state. In this case, the vacuum state's annihilated by all the A's, right? So the vacuum state is not, so it's annihilated by all the A's of all the Fourier modes. Right? And again, we can construct the excited states by acting on the vacuum with A daggers. Okay, we're acting on with A daggers at a particular momentum value, momentum space point. Okay, so I can construct multi-state, I don't want to call it particles yet. I can construct multi-thing states. Okay, and this state, if I can construct some multiple object state by operating with different A daggers, what I find is that the energy of that state is just the sum of the energies for each of those momentum configuration points. Okay. All right. And you can show that, and I'll probably have you do it in homework, the same way that you do in quantum mechanics, right? So that's you take you work out what the commutation relation is between the Hamiltonian and the A's and A daggers, right? And you use that relationship to derive what the energy of the state is. Okay. So it works the same way. There's just a lot more integrations and things going on. Okay. All right. So we know how to build these states, and so we know what the form of the Hamiltonian is, right? So we know what the eigenvalues are now, and now we want to ask ourselves, how do we interpret these states, right? And to do that, let's look at the total momentum operator. Okay. Last time we talked about the momentum operator for a classical field. Right, we found that it was one of the conserved charges of the energy momentum tensor, right? The stress energy tensor. Yeah, thanks. Right, and we found that the zero I component of this stress energy tensor looks like this, and it corresponds to the linear momentum. Okay. So what we want to do is we want to consider the vector form of that, so all three components, and then we want to promote it to an operator. Okay. So what we want to do is we want to look at this guy, right? And so we'll take this guy, we'll plug in our expressions for the fields. Okay. We'll do some algebra, and then see what comes out. Okay. And then from that, maybe we can infer something about what these, what are these states. Okay. So again, plugging in the expressions for the fields, and I do a little bit of algebra, okay? It's a lot of algebra, I'm just joking. And you get something that looks like what you would expect, right? When you compute the linear momentum operator and second quantization, or even just the simple harmonic oscillator, it looks like this. It's the number operator times the values, right? So this is exactly like second quantization, right? Except here we're doing an integral instead of summing over the discrete particles. Okay, so it looks a lot like second quantization, right? And so what we can infer is that this operator, this AP dagger, is creating momentum, right? It creates momentum P. And that P, because we're dealing with relativistic objects, gives us the energy, right, through the normal special relativistic dispersion relation, okay? And so just like what we saw for the multi-object state, when we computed the energy, when we operated the Hamiltonian on this state, and we found that the energy is the sum of the states, here we would find that the sum of the linear momentum is the sum of all the different states, okay? And that, again, you can show by using that P operator and the commutation relation between the A's and A daggers and hit it on that state, okay? Okay. So at this point, we can pretty safely say that we can call these things particles, right? And the reason we can do that, because now we're seeing that these excitations have, they're discrete entities, right? They're kind of just excitations in the field, but they're discrete, and they obey the proper special relativistic dispersion relation, right? So there's nothing wrong there's nothing wrong with calling these things particles, right? Well, the one thing you have to be careful of is that when we say particle here, we don't mean a particle, localized in space or in position space, right? We're talking, because our annihilation and creation operators are in momentum space, right? So in this sense, we're talking about particles, but they're in momentum space, okay? So that means we have particles that have well-defined momentum, right? But in position space, they're kind of a fuzzy quantity, okay? At this point, you can actually say something about the spin of these particles, right? So, and the way you do this is you can consider the two-particle state, right? So, two-particle state, I mean, by creating a two-particle state by operating on the vacuum with two different A daggers. Okay? And you notice that these creation operators, they commute. Right? The creation operators automatically commute regardless of their subscripts. Right? And so you can say, oh, well, this state is identical to that state. Right? It doesn't depend on how I fill the states. Right? I can fill it first with Q and then with P, or first with P and then with Q. Right? And in this case, the fact that these guys obey commutation relations, the A's and A daggers, it tells you that there's nothing stopping us from filling one particular mode with an infinite number of particles, right? There's nothing that'll stop us. In the case of fermions, we'll see that the anti-commutation relation means that if you try to put more than one particle per state, you're going to destroy that state, right? It doesn't allow you to do that. But in this case, there's nothing stopping us from doing that, okay? And if
they are the same particles, but with different momentum.
Well, what I'm saying in this last line is that I could set Q to P. So I could put as many particles into the P mode as I want. I can I can have a system of particles. I can give them all the same. Here we're only describing the states by their momentum, right? So you're basically saying that they have the same quantum numbers.
Yeah, I mean, they are both, for example, the same boson, like Higgs boson in this case.
Mm-hmm. Yeah.
Or it could be two different kind of bosons in nature.
No, here we're just dealing with one field.
Okay.
Yeah, so we're just dealing with one field. So we could fill these states, they're identical fields, and we could keep piling them up in this, in this P momentum state, and there's nothing to stop us from doing that, right? And those two facts, those two observations tell you that Klein-Gordon equations are bosons, right? They obey Bose-Einstein statistics, okay? And we know that they're scalars, they're spinless particles. Okay, so finally, I just want to end with how do we normalize these states, right? So, you're used to normalizing things in quantum mechanics, but here we have to normalize things in a way that we preserve Lorentz invariance, right? Because we want to have, we want our theory to be Lorentz invariant, okay? So what we need are, basically scalars or something that transforms, in a well-prescribed way, okay? So let me start with the vacuum. So the vacuum, you can just normalize, the same way that you do in quantum mechanics, just normalize it to 1, okay? The tricky part comes in when you start to talk about the one particle states, right? And by one particle states, I mean exactly that, where I hit the vacuum with 1 A dagger, okay? So that's how we define a one particle state. If you look in some books, they choose to go with the simplest normalization, which is this, okay? It's just a generalization of, the single, the normalization of single particle states in regular quantum mechanics, right? They're just replacing Kronecker delta with a Dirac delta, and again, that factor 2 pi cubed comes in because we're dealing with volumes, okay? But it turns out that this simplest normalization you can still use it, but later, somewhere along the line, you've got to account for the fact that this thing is not Lorentz invariant, okay? So either, when you computing some observable or, somewhere along the line, you have to put in a fix, right? Because this thing is not Lorentz invariant, and that's not a good thing, okay? So what we can do is we can either do that, which it gets complicated, or we could just fix it right now, right? And that's what we'll choose to do. So the way we fix it is to alter the definition of a single particle state, okay? And if you look in Peskin, he goes through the argument of how you come up with this. I didn't want to spend time doing it because it's just, it's just an exercise that, shows you, that you have to include some factor, okay? But it's in there, right? It's in his book. So what you do is you alter this and you include this factor of the square root of energy, basically, okay? And what that does is when you compute the inner product between two one particle states, those energies are going to cancel out some other energy terms. And what you find is that the correct one particle the normalization condition for one particle states gets altered by this factor of 2 EP. All right? And you can go through and you can show that, you can do a boost or whatever, some other Lorentz transformation on this thing and show that it is Lorentz invariant. Okay? So now that you have your single particle states correctly normalized, you can go off and compute, whatever observables you want and know that you're doing things correctly because you're Lorentz invariant from the beginning. Okay? Like I said, that can be shown, and anytime I say that can be shown, it sounds like a really awesome homework problem. Oops. Okay. All right. So that's how we normalize the states, right? So we've normalized the states. We interpreted, what these excitations are. They're fields, right? They're particles. Now what I want to do is talk about the interpretation of the original field operator that we started out with, right? And that is, so I want to consider the interpretation of this state. So this is the field operator in position space, right? This is in position space. And so I want to try to understand or try to interpret what this thing means. When this field operator hits the vacuum, what does it give me? Okay. So what I can do is I can take our Fourier transform and plug it in, right? And what's going to happen? Well, remember that the phi in momentum space has an A and it has an A dagger. Okay. So the A, when it hits that vacuum, it's going to go to 0. right? So the 0 goes away. The A dagger is going to give me a single particle state, right? That's what gives me this peak, okay? And you can see that I'm still integrating over these modes, okay? So this looks a lot like a linear superposition, right? So what we're saying is, the field operator in position space is a linear superposition of single particle states, and all those single particle states have well-defined momentum, right? Okay. Think about this in terms of, think about it in terms of quantum mechanics, right? You can always go back and forth between position and momentum space, and wherever you are, it's a linear superposition of the other space, states in the other space, okay? The one difference is here that we're integrating, okay? All right. And what you notice, so you notice that besides this factor of 1 over, so the 1 over EP is different, okay? That we don't have in non-relativistic quantum mechanics, right? But if we were to take the non-relativistic limit of this expression, right, what happens? That 1 over EP just becomes a constant, right? It goes like the mass, right? The rest energy starts to dominate. And so you can forget about it. You can just pull it out. It's just a constant, right? And then at that point, you see that it really is. It looks a lot like the relationship between position and momentum space in regular non-relativistic quantum mechanics. Okay. Right. So in the end, what you're saying is that this operator phi, it creates a particle at position x, and that particle at position x is a linear superposition of the momentum states. All right, it's like a wave packet. All right, it's just the field version of that. Okay, so these are particles. Those are the particles in position space. Those are the physical particles that we talk about. Right? And actually, you can confirm it if you go to compute this guy. Right? So if I take that one particle state and I overlap it with another p state. Okay, so what I'm doing is I'm taking that expression I had before and I'm flipping it over to a bra, right? And then I'm hitting it on a one particle state, right? And so what that does, so think about it in terms of non-relativistic quantum mechanics. That operator should produce a particle at position x, right? And then the overlap between x and p in quantum mechanics is what? This is the plane wave, right? So let's see what happens. So let's do that, okay? So I have my A's and A daggers in there, okay? I can cancel those factors of the energy, right? And I can do some algebra with the A's and A daggers. I can already see that this A dagger inside the parentheses, when it goes to the left, it's going to hit the vacuum state and give you 0, okay? So the only part that's going to contribute from that middle parentheses term is the first term, the A. So it's going to create a particle with P prime when it acts to the left, right? That's going to give you a delta function. You'll end up with a delta function, which will allow you to do the integration. And sure enough, you find that, when I get done and the smoke clears and everything cancels, I end up with a plane wave, okay? So we have the correct interpretation. So this field operator is creating a particle at position x, and when we overlap that state with a momentum state, we get a plane wave, right? Which is what you get in non-relativistic quantum mechanics, right? Okay. So this is just the position space representation of a single particle wave function of the state P, okay? So it's the same thing, all right? So it works the same way. All right? So that takes us to the end of my talk, okay? So I'm about 35 minutes short. But so I'll get caught up on the slides next time. Next time, which will be, I guess, a week from today, right? Because of Labor Day. We won't have class on Monday. But next time we'll finish up talking about the Klein-Gordon field. We'll talk about the propagator. We'll derive the propagator, and then we'll start a discussion on the Dirac field, which will be the main entity that we want to work with this semester. Okay. I'll put these either on a website or a Dropbox and let you guys know. Okay, these notes. And I'll start to think about some type of homework set too. Okay.
Like PowerPoint or handwritten?
What do you mean? Huh?
Dropbox notes that you're gonna put in the Dropbox.
Yeah, I'll put the PowerPoint in there. Yeah. Okay. Any questions from Brownsville?
Do you have our emails if you're going to send it?
Yes. Yeah, you're on my roster. So when I send emails to these guys, you guys will get them too. Okay. But I'll let you know in the very near future of any news. All right. All right. Have a good weekend.
Thank you.